Well, ladies and gentlemen, good evening. It's not every day I get a chance to speak directly after the Director General of CERN has handed out certificates to the students who've been participating in some of our programs, but it's a very remarkable week in the city of Melbourne, I must say. My name's Professor David Jamieson. I'm the head of the School of Physics, and it's my privilege to be the compere for tonight's program. This event is the first of our July lectures in physics for 2012. Sorry, can I just grab the remote control? Thanks. Let me just say, before we begin the formal part of the proceedings, we all know that the World Wide Web was invented by the people who brought us also the Higgs boson this week. And therefore, I have to ask you, because I'm sure you've all got a smartphone or equivalent in your pockets, to please turn them off for tonight's proceedings. And I should also say that we are videoing and recording the proceedings tonight, so please keep that in mind if you get a chance to ask a question at the end, because your words will be recorded forevermore. At the end of the program, I'll put up again the remaining events in the July Lectures in Physics program for 2012. So tonight is just the beginning. So let me just say a few words about the July Lectures in Physics. These have been running every year since 1968. And in case you missed the previous 44 years of July Lectures, here's a quick overview of the major key words that we've covered in that long program of outreach activities for the people of Melbourne and beyond. And I must say that this year's program, and particularly tonight's program, unites all of the big themes that have featured so prominently in our July lectures over all those years in a most spectacular fashion. And it's been a really, really big week for physics, as you've surely noticed. On Wednesday afternoon, we had one of the biggest announcements in physics for probably 100 years, evidence of the remarkable discovery of a new subatomic particle, the highly anticipated and eagerly sought Higgs boson. So tonight's event takes advantage of a rare alignment of historical forces. First, of course, is the announcement of the discovery of the Higgs after decades of work by legions of people from all around the world. But the second is the privilege of the city of Melbourne hosting the major international conference for high-energy physics. It's worth saying a few words about the history of how this came to be, because actually the people here in Melbourne put in a bid to host this conference for 2010. Unfortunately, a bit like bidding for the Olympics, we didn't get it and it went to Paris. How fortunate was that? Because here it is, the world's high-energy physicists are in fact gathering right now for the conference in Melbourne in 2012. So this international conference has been brought to us thanks to the efforts by my colleagues in the Australian Research Council Centre of Excellence for Physics at the Terascale. That's tera as in terabyte for the rest of us, and that's high-energy physics for everyone else. The conference is the peak event for high-energy physics. And we always hoped that CERN would have some interesting results to announce in the opening session of the conference, and sure enough they did. And ever since the big announcement on Wednesday, we've been on a roller coaster of activity. So the big announcement was made on Wednesday evening, and Rolf and his team made the announcement in Geneva and must have gone to the airport directly afterwards to be here today and shared with us the global limelight for the announcement of the Higgs boson. So tonight's panel is actually comprised of distinguished delegates to this big conference. And so tonight, ladies and gentlemen, we have the rare opportunity to hear directly from the people at the front line, the people whose hands are on the levers, who have brought us this huge result. So to begin, I'm going to announce our four panellists and invite them to say a few words about, first of all, how they got into high-energy physics, what it is that motivates them, and what it is like to be part of this team. So our first speaker is going to be Professor Albert de Roeck, who is the deputy spokesperson for the CMS experiment. And the CMS experiment, CMS stands for Compact Muon Solenoid, one of the two big experiments that was part of the announcement this week. Albert is a professor at the University of Antwerp in Belgium. He has a visiting position also at the University of Durham in the UK and the University of California at Davis in the USA. He comes to us with a PhD from the University of Antwerp and a career in high-energy physics in the experimental program. He also has spent quite a bit of time in the high-energy physics laboratory in Germany. Second, we're going to hear from Dr. Stephen Goldfarb. He's also a physicist based at the University of Michigan, and he has a role as the Outreach and Education Coordinator for the ATLAS experiment at CERN, the other great experiment that was part of Wednesday's announcement. ATLAS, of course, is from Greek mythology, but you can also consider it standing for a toroidal Large Hadron Collider apparatus as well. Steve began work at the University of Michigan and he has served in many leading roles as part of the high energy physics program, particularly the Muon project. And behind all of the hardware, of course, and symbolised by this image is a whole pile of software. I had the pleasure of visiting the computer centre at CERN late last year. You could go up to the window and you could warm your hands from the heat pouring off those thousands, indeed millions of computers that are crunching the data that are paired also with computers all around the world, including a substantial number in the University of Melbourne data centre right here. He also manages some of the outreach programs that engage students with the CERN program. Third, we'll hear from Professor Raman Sundrum from the University of Maryland in College Park in the USA on the east coast there. Raman is one of the world's most highly cited physicists in recent years. His research is actually directed at what happens next, what lies beyond the standard model: extra dimensions, supersymmetry, strong dynamics, unification of forces, and dark energy. And I've just confirmed with Raman that he did some undergraduate study here in Australia at a university attached to a major coastal city to the north of us. But he did his PhD at Yale in the United States and has done postdocs at some of the leading US universities, including the University of California at Berkeley, Harvard, Boston University, Stanford, Johns Hopkins University, there were more than one John, and now at the University of Maryland. And our fourth speaker will be Professor Young-Kee Kim, who is the Deputy Director of Fermilab, which is the great and friendly rival to CERN in the US, to show that we're very broad-minded here. Young-Kee's research is in experimental physics and focusing on understanding the origin of mass and the fundamental particles. She has undergraduate degrees from Korea and a PhD from the University of Rochester in the US. She's been the Deputy Director of Fermilab since 2006 and has been a spokesperson for one of their most important and successful experiments that coordinates some 600 physicists from around the world. She's also earned many medals through her career, not the least of which have been the Rochester Distinguished Scholar Medal and the Professional Opportunities Award for Women in Research and Education from the peak science body of the US, the National Science Foundation. So now let me turn to the panel. Perhaps we'll start with Albert. And I will invite Albert to say a few words about his role in the great project, how you came to be part of it, and what it's like to be part of the team. Albert.
Okay, thank you very much. It's actually a great pleasure for me to be here and see this room full of people sitting on the stairs like we did a couple of days ago when the Higgs was announced at CERN, and also with the simultaneous broadcast we had here. So let me tell a bit what my role is in all this. First of all, I should say this is really something novel for me what I'm doing now. I'm giving a talk where I had the right of having only one transparency, and that's the transparency you see there. And that's actually what could be a Higgs event candidate. So, what happens and where we come in, and so let me introduce the thing. Myself, I'm from Belgium, but I work at CERN, which is an international, but particularly European-oriented in terms of people that work there, organization, as far as the accelerators are concerned. At CERN in Geneva, Switzerland, we have a big machine. A machine that is 100 meters underground and 27 kilometers long. It's a tunnel of 27 kilometers in a circle. That's the accelerator, called the LHC, the Large Hadron Collider. Hadron is a type of particle, but large and collider, I think, are clear what it means. So, what it does is we have in that machine two beams of particles, in fact protons which are part of the atoms. The nucleus of the proton is made of the atom is made of protons and neutrons. The proton is charged, we can accelerate these. And we can make them go opposite direction until certain points where we make them clash on each other. And then that happens. What happens actually there is that here we have Einstein at work. Einstein's most famous formula, which is actually the most famous physics formula known in the world, I presume, at least in the northern hemisphere, but I presume in Australia as well, is E equals mc squared. Energy and mass are related. We use the energy of that big machine, which we have, which is the highest energy we can create at this point in time in the lab, to create mass, to create particles coming out. There are two protons hitting each other, but you see many particles coming out. And in fact, we can produce heavy particles, much more heavy than the proton, because we convert the energy of the beams into mass. This is how a collider works. And that's needed, because the particle we are actually looking for, we knew is a particle that's going to be heavy, much more heavy than a proton. In fact, 125 times more heavy than the proton, as it turns out. But we did not know even in advance where exactly it would be. Now, what is this particle? This particle, well, details will be surely more explained by my colleagues when they come here, but one important thing of this particle is to think as the following. It's actually teaching us something from the beginning of the universe. If we were at the beginning of the universe in the hot, dense soup of energy and particles that exist at the time, in the very beginning, particles were zapping around with the speed of light. That's very fast. That's 300,000 kilometers per second. Not much can happen to solidate, for example, being sitting here around. We would be all zapping around 300,000 kilometers per second. If not, some mechanism, something new was introduced that is slowing down things. And typically mass, as we know it, is an object that slows down, that resists to speed. Big trucks, get on that speed much more slowly than a motorcycle, for example. So, to have at the end that we are not having particles moving around with the speed of light, with this very fast speed, something had to be introduced in the very beginning of the universe. And that's the Higgs. But that was a postulation. We did not know that for sure. In fact, Higgs, Professor Higgs, when he formulated his theory in a broader context, that's already almost 50 years ago. He came up with the idea, because it's a mathematically very nice trick to do that. But theories are only worth something when the experiment actually confirms the theory. And therefore, CERN as a laboratory and other laboratories before, like Fermilab, as you will hear, have been on the quest for this particle. We call it actually among us the holy grail of particles to look for. People outside for us call it the God particle. We don't like that term so much, but I'll leave it to my colleagues to explain why we don't like it so much. And so how these experiments come about? These experiments come about built around colliders, like I said, like now we have the largest one in Geneva, which made it possible to actually see this particle after only 2 years of operation, in fact. But particles is not enough. An accelerator is not enough. You need something that measures what is being produced. So you see, visualized what's coming out there. These are detectors. And the detectors we have for this project are huge. In fact, neither of the two main detectors, I represent one and the next speaker represents the second, would fit in this room. They are so big. And to give you an idea, the number of people that work in each of these experiments is over 3,000 to get this experiment to work, build it, operate it, and look for things. And the Higgs is one aspect we look for. It's one of our main aspects, but there are also other things we look for. So 3,000 people. Of the 3,000 people, at least in my experiment, somehow like 700 were on the hunt for the Higgs. This is more than the number of people in the room here. Physicists all hunting for the last few years, searching for this particle. And the last 4 or 5 months, many of these people did not get much sleep. Because we had the target. We had the target, and that was this conference here. And people were really looking, analyzing the data, looking for events, as we see there. And it's basically the green outcoming sites on the side, which are the photons which you see, which are a signature for a candidate of a Higgs particle being produced there. I simplify because it's much more difficult to find it in here. And in fact, we have billions of events collected, billions, tens of billions of events. And only about 100 of these collisions, of these 10 billion collisions, contain actually something interesting, which could be the Higgs particle. We saw some first hints last year already. And now we needed this year to have a real good set of data to actually come to what we see now. And we were, of course, extremely happy that when, just before the conference, I knew it like 2 weeks before you that we saw the Higgs, but not much more. So then we were sure we had it, and we could go out and present it to the community here. And just to finish, I thought that once we've done that, we can actually take a rest and sleep. But the last 2-3 days have been very, very hectic. And so, yeah, I'm happy that we are there. And you know, I think I will stop there and leave the floor to one of my colleagues.
Albert, thank you. Thank you very much. So, Stephen, over to you. And perhaps I could ask you to start in outreach mode and give us a quick explanation of what a Higgs boson is and why is it important. Please.
Educate. Okay. Okay. Thank you. Okay, so first of all, I'm very fortunate because Albert told you everything. So I can say whatever I want now. Atlas is the experiment, as was already explained by Albert. There were 4 different places around this ring where there are collisions going on. CMS sits on one end, and completely opposite is the Atlas detector. And we've been keeping separate from each other for the past several weeks because neither one of us actually wanted to see the other's data. That was rather important because these 3,000 people on CMS, 3,000 people on Atlas are probably the most important differences in these experiments. That being that you have a completely different set of people working on a problem and using their ideas, using their thoughts, their own ability to think, coming up with how to measure this beast, this particle. Keeping them separate was great, and we did not want to see what the others were doing because that might have biased us. So we only found out, and we were with all of our colleagues all together when we saw each other's results a few days ago, and that thrilled us. But what was more thrilling to me was just after that, seeing the excitement on the faces of people who didn't know anything about particle physics. Seeing the headlines, seeing a place like this filled with people who want to know what's going on, what are you doing? That amazed me. So I'll put on my education and outreach hat for you because this is important. This is big, and everyone seemed to recognize it as being big. We do find particles from time to time. CMS has already discovered a particle recently that you didn't know about. Atlas found one. Our friends at LHCb, another experiment on the ring, on the LHC, also found a couple, but you guys might not have even noticed it in the news. It was because we knew they were coming. We have a model that was so good. These theorists, we hate it when they're right, but they've been right for 50 years. And they gave us a beautiful model, and with that we could predict things. So when we found these other particles, we weren't surprised. We knew what their masses were going to be. We knew that they were going to be there. That's pretty amazing, actually. But what happened just recently, a few days ago, was really incredible. That someone could come up with the idea of a mechanism that gives mass to other particles, something to explain a problem in a way which us experimental, well, maybe a few of the smart experimentalists like Albert can understand, and give us concrete things that we could measure to look for it doesn't happen that often. The beginning of this model was back in the early 60s, when we decided that electricity and magnetism could be joined with a nuclear force. That was a brilliant step forward. But even more impressive was that by adding this Higgs mechanism, they predicted some particles, some carriers of force, at exactly their right masses. And that began, I call it sort of the miracles of the Standard Model, but it also turned us into, well, somewhat blasé physicists. We got used to it very quickly. They predicted in the 80s that we would, in the 60s, they predicted that we would find a couple carriers of the force. In 1983, we found them at exactly where they were supposed to be. From that time forward, we've been able to do that. And one of the things that's always amazed me was that we were so confident at the end of the running of the accelerator before this. We called up our friends in Chicago, where there was another accelerator being built, told them, congratulations, you're building an accelerator, and that accelerator is going to find the sixth and final quark, and here's what its mass is going to be. And they said, okay, thanks, and then they found it, and there were no headlines. There weren't people. We were interested. We were definitely interested. People in the physics community wanted to know it. But what they started doing right away with it was saying, okay, now that we know that, which we already knew, but now we have a measurement, now we can start trying to find the Higgs, because that will help us to do it. So it was known that it would be there. That was because of this work, because of the theorists, because of the work of Higgs and Englert and Brute, that we were able to make these predictions. And finding that particle, though, that marked, I think, the biggest step. A huge step. And I'm not going to go complete detail about how it works. Essentially, you have a field. When a particle goes through that field, it accumulates mass. How much it couples with that field is what gives a particle, an elementary particle, mass. If it goes through easily, it has less mass. If it, like a truck, it's going to get more mass, etc. And this particle that we found, the Higgs particle, is just a manifestation of that, something that helps to get the idea through. I think I'll let the theorists explain exactly how the mechanism works. So what I would like to say, actually, which I think is very important about all this, is that I'm very happy that everyone has recognized the significance of finding this. We don't like to call it the God particle. In fact, you should know, if I dare say so, that the actual name that was given to it by Leon Letterman was the goddamn particle, simply because he'd been looking for it forever, and we have been looking for it forever. And we hadn't found it. But the publisher of his book refused to call the book the goddamn particle. And so we got stuck with this thing. We're not so pretentious. We're very humble about looking for work. We're humble in many ways. And one of the ways is because we know that we're representing all of you. Every single one of you has played a major, major role in this discovery. Every one of you, because of your enthusiasm, because you are interested in science, you want things to happen in science, you express that enthusiasm to friends, you get them excited in science. That's what keeps the world doing what we're supposed to do. Human beings, when you look at them in detail, you'll see that they have a few things they have to do. And one of them is they have to eat. Another is they have to make babies. And a third is that they have to understand the world around them. It's just inside us. We have to do that. Let's face it, we're slow. We're tasty morsels. We would have disappeared a long time ago if we didn't do that. It's essential to our species that we do the work that we're doing when we do this research. And I think that's why that resonates in everyone when they see that we've made a fundamental discovery that suddenly has allowed us to understand the universe more. We've done something for our entire species which will allow us to continue more. It will allow us to have a better view of what we have to do next. It's a major block in our understanding. Human beings, by doing basic research, do a few things. One is to add information, knowledge about what we've done. We add that knowledge up and that accumulates and we can do things on top of that knowledge. But I think even more so, more important than that, there are times in history where we change the way we think. And that's what's exciting. And it's hard to recognize these, but sometimes there's these people like a simple patent clerk who says, hey, if something's going close to the speed of light, it doesn't behave like we normally see it. It does something different. It doesn't behave like you normally see things behave. Okay, when you're walking around, you don't go close to the speed of light. You suddenly have to think differently. The same thing happened when a friend of his, Niels Bohr, came up with this really strange idea about quantum mechanics. A whole different way of thinking. And this gets reflected in all of the things that we think about after that time. By finding and understanding that the Higgs mechanism is correct, and we don't yet know that. We think we're going to know that. We don't yet know that for sure. We know we found something and it looks a little bit like the Higgs and smells a bit like the Higgs and we think it's probably the Higgs. We'll know that soon. We have to do a few more measurements. But once we have that, we've made that major advance. We have a bit of knowledge, but we also have a way of thinking about the universe that's confirmed. And it's different than what we had before. And so I think that's a major, major thing. And I want to thank all of you for supporting our research and ask you to please continue to have the enthusiasm to support what we're doing.
So I'd like to hand the microphone over to Raman here. You've published a number of papers with Lisa Randall. In fact, these papers have become so famous, I think they're just known by the initials RS number 1 and RS number 2. And some of the present company may have heard Lisa Randall speak here in 2005. But can I ask you to give us a bit of an overview, and in particular, what is this supersymmetry? And more particularly, we've heard a lot about the Higgs boson. There are two guys there. Higgs, we've seen a lot. But who was this other guy, Bose? Please.
Okay, so I have my prepared remarks, but I'll try and answer those questions as well. So I'm the only guy on the panel who actually brought my equipment with me. So I'm the lone theorist here. So let's see. I'll answer those questions in the context. I wanted to say a few things about the specifics of the discovery, but also really to just put the discovery in context and maybe provide some ammunition for questions. And I should say that particles like the Higgs boson or the top quark, these are for us the sort of alphabet in the story that we tell. And like a professional calligrapher would love each particular alphabet, we love every particular particle. And a lot of attention is spent this week on the discovery of this one new alphabet, the Higgs boson. But besides their sort of individual character and distinction, I think their true significance is in their collective behavior. Okay, so with the 26 alphabet or letters of the alphabet, you can write Shakespeare. With the letters of DNA, we can create, or life knows how to create itself. For us, particle physics is really the idea of cracking the genetic code of the universe, okay? The basic laws through which it is constructed and evolves. And there's an emerging theme that we've now seen over decades of research, roughly about a century of research, which is that a lot of the macroscopic diversity that we see and are part of is really underlain by a really shocking unification of energy and matter. And this unity is something that when you appreciate it is something very beautiful, okay? It's like great music, great art. So one question of where, I think all of us were asked how we got into physics is when I was an undergrad at Sydney Uni. Oops, I've let that out of the back. I think it was in my, what we'd call in America the junior year, but here the third year of undergrad, where I had to do an essay or something, and I ran upon the mathematics of this subject, particle physics, and it blew me away. And I didn't actually know there was a subject called particle physics, even though I'd been studying physics for a few years by then. And I asked around, and they told me that, yeah, this thing has a name. It's called particle physics, and that's sort of how I got into the subject. But basically, the grammar of this subject is given by quantum mechanics and relativity, these two bizarre things that, however, give us everything that we take for granted. And it's really striking the continuity of effort that physicists have put in decade after decade to try and understand this beautiful unity that underlies the diversity that we see. When I was a kid, again in Australia, I was very taken by creation myths. I used to read about Greek mythology, Indian mythology, Norse mythology, and about how the universe came to be, as told by people either hundreds or thousands of years ago. And of course, the forces of nature were always a sort of family of contentious gods. And in particle physics, what we found is that there's something like that. The forces of nature actually have family-like relations, and there's even a kind of a family tree that seems to be emerging. The Higgs boson is significant because it's part of what we'd call electroweak unification. And basically, the youngest of the forces that were born soon after the Big Bang were electromagnetism and the weak nuclear force that underlies radioactivity. And we have sort of very compelling evidence that they fit into something called an electroweak unified theory. And of course, if you say that there's some sort of unified theory, then why were we ever talking about electromagnetism and the weak nuclear force as two separate things? And the answer is because this fundamental unity is hidden. It's partially hidden. It's only partially hidden so that with enormous detective work, we could figure out that there was actually a unification. But there has to be an agent that hides it. And basically, this unity, fundamental unity, is veiled by an all-pervasive field in space. And that's the Higgs field. Okay? That's its significance to me, is that it's covering up, hiding a little bit, this great truth that there's unity between the electromagnetic and weak forces. This field sort of came into existence in our universe very in the few instants after the Big Bang, as the universe expanded and cooled. And it came into existence in the same sense that if you take water vapor and you cool it, it condenses into liquid water. Okay? So some sort of cooling like this happened in the early universe and gave rise to what's called a Higgs condensate. So let me just say a little bit about what I make of the discovery. I think, you know, the job of actually testing this fantastic story I just told you is really to try and isolate the sort of Lego block of this Higgs field that, as I say, pervades all of space. We are like fish in water, asking, where's the water, okay? And the idea is you want to isolate one atom of it. And the Higgs boson, a single Higgs boson particle, is the particle that makes up the Higgs field, very much like photons are the quantum particles that make up an electromagnetic wave or light beams. The name boson actually comes from the physicist, the Indian physicist Bose, who played with Einstein a crucial part in determining the behavior of at least half of the particles of nature, the so-called bosons. And they have a special property. They can be put into a special state that creates force fields. So when we discover the Higgs boson, we're actually discovering a new force of nature. You were taught in high school probably that there's electromagnetism, the weak nuclear force, the strong nuclear force, and gravity, 4 forces. Well, this week we got a 5th force, and that's the Higgs force. It's a short-range force like the weak nuclear force. And it's very exciting, okay? The high school books have to change now. So, have we really got it? Well, I would say no. To be more cautious, we've found a particle. And this particle is a boson. And the evidence strikes me as being reasonably compelling that it is a Higgs boson, meaning it plays this role of veiling electroweak unification from the naked eye, but not to expert detectives like the experimentalists. If you often hear called the Higgs boson, and the refers to what I call the minimal standard model, the theory which discusses all of this in the fewest moving parts. But we don't really know yet that it is the minimal theory. And in fact, there are reasons to think that maybe we go beyond the minimal theory. And I just want to quickly sketch a few reasons that maybe might elaborate in questions. So, for example, again, taking the cosmological evolutionary point of view, we know, or we have very, very strong reasons to believe, that matter and antimatter, which are sort of twin species born of relativity and quantum mechanics, had a war of mutual annihilation in the very early universe, okay? Almost all the matter and antimatter annihilated each other into pure energy, but a tiny sliver of matter survived this war, and all our galaxies and all of you are made of that tiny sliver. And we'd like to know what tipped the balance in this almost perfectly matched set of evil twins fighting it out in the first moments of creation. And it may well be that the process of Higgs condensation I talked about earlier is crucial in understanding what tipped the balance, but only if the Higgs structure is non-minimal. Okay, so we're very eager to continue experiments like this to find out whether that's the case or not. When you find a new force, like the Higgs force, you can ask, what can you do with it? And one of the things we'd like to do is use it to catch dark matter. So we know that most of the matter in the universe is actually not made of the usual stuff you and I are made of, electrons and protons and neutrons. It's made of something we don't actually understand yet. But it's possible that the Higgs force is something that we can use in dark matter detection to catch it. And this week, we finally know the range, the incredibly short range of that force. A couple of more things. We also know that the Higgs mechanism is a prototype for an even grander unification. In fact, we just call it grand unification, for the unification of electromagnetism, the weak nuclear force, and the strong nuclear force emerging at an even earlier instant after the Big Bang. And we now know, because of the mass of the particle seen, if it indeed is a Higgs boson, and I say the evidence is reasonably compelling, that the mass of about 130 proton masses is favorable for this kind of grand unification scenario. Whereas, for example, if the mass of the Higgs boson had turned out to be, say, 500 times the proton mass, which it might have been, then that would have been disfavorable for this idea of grand unification. So the details that we're learning really matter to the huge story of cosmology and basically the way the world works and the story of unity. There are other ideas out there. For example, when people study the minimal standard model, theorists see a kind of imperfection, which I can discuss in question time, but basically there are reasons to think that there's an enhanced structure. Ideas like supersymmetry are one such structure. Supersymmetry is, again, an addition, a possible conjectured addition to the grammar of particle physics, the grammar being set by quantum mechanics and relativity thus far. Supersymmetry is a very beautiful possible addition to that grammar, which would help us understand aspects of the standard model which are still mysterious, the so-called hierarchy problem. The discovery of the Higgs, or whatever this particle is, at the mass that it is actually vaguely troubling for the idea of supersymmetry. So a lot of us theorists are wrestling with how to accommodate in supersymmetric theories the exact details of this discovery. Finally, I should say that the actual mass that this particle has shown up at is actually very opportune for studying, for hunting for new types of physics, because this particle decays, and we can see it decay, in a number of different possible ways. And it can be produced in a number of different possible ways, which are roughly competitive. So we can study, it's like both being able to see you and to hear you, and if you're close enough to smell you, that if you have enough different ways of sensing something, you have a much better image of what it is. And at this mass, that turns out to be very favorable. So we're very excited to be able to study this in great detail as we move forward. Let me just say on the side of the human achievement, just finally, that this is really an incredible and I think a long-lasting human achievement. I mean, it'll be something that is known 300 years from now, when American politics and the presidential election and so on have gone away. So I think to me, it's as shocking as this particle is. I'm really also equally shocked by the perseverance and ingenuity of the physicists in pulling it off. And remember, this is something that is being sustained over several generations. To me, that's like, creating a kind of modern pyramid dedicated to human understanding. And we don't have a pharaoh to say, you better do it. So really, this had to contend with governments changing many times, funding, public sentiment, politics, all of that. And yet in this case, against all those odds, international cooperation triumphed in a way that I find just mind-blowing as the physics itself. So congratulations to those who pulled it off, and I'll stop right there.
So now I'd like to invite our fourth panellist forward, Young Ki. Perhaps you could tell us something about the pathway from Korea to Fermilab in the USA, and something about the great and friendly rivalry between the two labs.
Okay, so as you can see, I am short. So actually, I was very pleasantly surprised to see so many Asians in this room and also in the Melbourne city around. So this was quite surprising and also very pleasant. So, you want me to say about my pathway? I don't want to say so much, but I was born in South Korea in a small village with 4 sisters and 1 brother, so big family. But anyhow, I grew up at countryside and went to high school in bigger city, and my college education was the biggest city in Korea, so that's Seoul. Then I came to United States from my PhD. So that's how I came to United States for my the PhD degree and now I'm teaching at the university and also a deputy director at Fermilab. Fermilab is the U.S. national laboratory primarily dedicated to particle physics. So you heard from David that there's some rivalry going on between Fermilab and CERN. So let me tell you a little bit about Fermilab. First of all, you saw all the standard model elementary particle list in the previous slide. Out of all those particles, Fermilab discovered 3 particles. One is, if you remember, there's 3 kind of neutrinos. In the table, it was a kind of 3. It was there. So 3 types of neutrinos. By the way, these neutrinos are everywhere in the universe. In fact, every second, about trillions of neutrinos zip through your body every second. But you don't feel anything, right? It's because they are very, very elusive. So there are 3 kinds, and tau leptons, the last one, was discovered at Fermilab year 2000. And we have, by the way, many kinds of accelerators simultaneously running because we are doing different kind of the physics, the particle physics research and using different kind of accelerators. So we have, in fact, the world's most powerful and diverse neutrino beam accelerators still going on. And secondly, we discovered the bottom quark. You'll see B, spelled B. That was discovered by Leon Lederman in 1978. And the top quark, which is the heaviest quark ever observed. So you heard that Higgs boson mass is about 125 times proton mass. That top quark mass is about 172 times proton mass. So you see how heavy that is. However, these particles are so-called fundamental particles or elementary particles. That means they are the smallest things we ever seen. And they are not made of even smaller things. So at the scale of how small they are smaller than, nanometer is a tiny. We are talking about nanometers. So that tiny scale size particles, but its weight is huge. The top quark case, as I said, about 172 times the proton mass. So these are the 3 particles that Fermilab discovered. But going back to a little bit, we talked about this God particles. So I'm sure that there are many stories. By the way, this is the book called The God Particle, written by Leon Lederman, who discovered the bottom quark and the second, the neutrino, muon-type neutrino he discovered, and he got Nobel Prize. And he was the second director of Fermilab. So, of course, a God particle, I'm sure that's one story, and I'm sure there are many stories. But one of the stories I think he said to us is that the publisher of the book, after he wrote it, he said that if you call it God particle, then probably many people will buy the book. So it's a purely economic reasons. That's one story. So I don't know which is a really true story, but anyway, that's that. So I said the number of the accelerators simultaneously running at Fermilab, but one of the accelerator was called Tevatron. This is a predecessor of LSC. The size-wise circumference is 6 kilometers. LSC is a proton and proton collider. Tevatron is a proton and its antiparticle called antiproton. So proton and antiproton collider. And the energy is about factor of 4 times smaller than LSC. But of course, Tevatron was a predecessor of LSC, and it started running 1985. We completed its operations year 2011. In fact, last September, we turned it off because we have a now bigger and more powerful machine, LSC start running. Talking about the antiproton, I don't know, you're probably very familiar with the movie called Angels and Demons, right? So there's a lot of antimatter there, right, in the movie. Who made it? Where was that film located or filmed? It was at CERN. In fact, the not CERN, but Fermilab is the one who produced the most antiparticle. But anyway, so that's the story. So yes, there was a little bit of rival, even though Tevatron was an earlier version of LSC, and LSC is certainly more powerful. But several things that I can say about Tevatron's contribution to this particle, Higgs boson. First of all, I told you about top quark, which was discovered at Fermilab, and another particle, which is quite heavy, but not as heavy as top quark, about half of a top mass. That's called the W boson, which was discovered at CERN in 1982. These two very, very massive particles, so we studied in details using the tevatron. In fact, we measured its mass of top quark and mass of W boson very, very precisely. By doing so, if you use the standard model of particle theory, we can predict the mass value of a Higgs boson. Unfortunately, we cannot predict very, very accurately, but we can give a sort of a range of mass where Higgs should be if a standard model is a correct theory. From that measurement, tevatron concluded that Higgs boson should be less than about 140 times the proton mass. And let's discovered at Higgs mass of 125 times the proton mass. So we agree quite each other. So that's one contribution that tevatron made. And that also tells us that so far standard model of particle theory works very well. Another contribution that tevatron made regarding Higgs, the discovery of Higgs, the field, is that the Higgs at 125 times proton mass, that mass range, the Higgs can decay to all different kind of daughter particles. In fact, the standard model can tell you Higgs can decay to this set of particles, the rate, and then another kind of a daughter particle is a different rate. So standard model can predict exactly how often Higgs decay into each decay mode. And the LSC, Atlas and CMS discovered Higgs boson in the 2 decay modes. And Fermilab, so tevatron, actually is very strong and sensitive to looking at another kind of decay mode or daughter particles. And then we looked at it, in fact. Then we found a quite tantalizing hint of Higgs decaying to that specific final state or daughter particles. And also mass of the Higgs was consistent with the LSC discovery. So that's another the contribution that the tevatron has made. Right now, tevatron shut down, and we continue to run the accelerators that we have been running, but even much more enhanced, more capable machines right now. By shutting down tevatron, we can utilize some of those components and enhance other kind of accelerators. As I mentioned, that we have a very powerful, diverse, very intense beams of neutrinos, and that intensity is even much greater right now than before. And then we are also creating new kind of particle beams to study other parts of the particle physics. You heard a little bit that the standard model itself so far works beautifully. There are many measurements made at the laboratories and explained in this framework of standard model. However, it does not explain number of big questions. You heard that dark matter cannot be explained by standard model. Another big discovery made about 15 years ago is that the universe, which has been expanding, and we thought maybe the expansion slows down, but it turns out it's accelerating. They could be related to a new kind of energy. We call it dark energy. Or it could be just a lack of our understanding in the gravity. But nevertheless, we have to understand that, and that's a big question. Another question, why the universe that we live in is dominated by matter, and what happened to the antimatter. That kind of questions really remained, and standard model cannot answer. So Fermilab's these new accelerators really going after number of questions that cannot be answered by standard model, which is the things we are doing at Fermilab cannot be done by the Larger Hadron Collider. So that would be my statement.
Okay, well, ladies and gentlemen, we've heard about people who use beams for a living, beams of protons, beams of antimatter protons, beams of neutrinos, and I think beams of ideas flowing from the tip of a pen. So now it's over to the audience. You can beam your questions down to the panel. There are roving students in the audience who have microphones, and so can I ask you to speak loudly, but wait until the microphone arrives before you ask your question so everybody can hear the question. I think the first was the lady in the black hat over here.
Thank you. Good evening. I have a question about the relationship between the Higgs field and the gravitational field. I understand a little bit about the Higgs field giving particles its mass and a bit about the gravitational field depending upon the amount of matter in a celestial body. What do we know about, or what can we imagine about the relationship between the Higgs field and the gravitational field?
I should have warned the panel that the audience in Melbourne is very well educated. And this is an excellent question. Can I invite a panelist to respond? Okay, Raman.
Yeah. Okay. So indeed, the Higgs field is responsible for giving all of the elementary particles that we've seen to date their mass, except for dark matter, which is an entity unto itself. And gravity is the thing that responds to that mass as well as to energy. Now, are they related? Are these two different types of fields? And I should say gravitons, which are part of the gravitational field, are also bosons in this regard. So we have Higgs bosons and graviton bosons, but are they related in any way? At the moment, based on what we see in experiment, they are not closely related. If you take, there's a continuity of research between people really doing accelerator design all the way to the string theorists mulling over questions like you ask. And so at that speculative extreme, then yes, there are certainly speculations, which I think are reasonably founded, that there is truly a unification of all the different fields, Higgs field and gravitational field, into a kind of unified field or even string theory. But it's very, very far removed from experiment right now. And so it's not something that, people spend a lot of time focusing on. But string theorists have certainly had ideas that unify both kinds of fields.
String theory. Okay, I call for another challenging question from the floor. I think the gentleman in the aqua windsheeter up the back.
When we talk about the Higgs field imparting mass to the particles, are we talking about the rest mass or relativistic mass?
Rest mass.
Short answer, thank you.
Okay, the gentleman in the very colourful top there, yeah. And perhaps if I could ask the questioners to keep their hands up, and then I can point to the next person and we can get the microphone up to save time.
As an ex-altar boy, I'm wondering how many gods were harmed during these experiments. And I was amazed that the two labs were competing with each other. Does that mean there were no peer-reviewed papers produced up until this point?
The fact that we work separately, you mean? We have like 100 peer-reviewed papers already published, but not on the Higgs. That's what we were waiting for. And so actually now the scientific publication is in preparation, and we have sort of agreed with each other, gentleman's agreement, although your spokesperson is actually a woman, but gentlewoman. Yeah, that is a gentlewoman, that we will publish at the same time, because now we saw the data we have is so similar, and that's a striking thing in science. You have to do 2 experiments, you get the same answer out of that with complete independence, which is absolutely essential in a scientific procedure. But as I also said, we do many other things, studies of these collisions and their properties and so forth, looking for other kind of phenomena, which also Raman was mentioning, which we should be looking at. And this we have been publishing throughout already, so there are peer-reviewed papers. But the paper on the particle is coming probably by the end of this month for both collaborations.
Could I have some further questions? I think we've got one lined up ready to go, and I think this gentleman next. So over here first.
As I understand it, and correct me if I'm wrong in a way which minimises any personal embarrassment, but as I understand it, this experiment has raised from the field a particle which required the recreation of conditions which only existed in the moments after the Big Bang. In recent years, several theories of the universe have been put forward which don't involve a Big Bang. Some string theorists have talked about higher dimensional brains colliding, kick-starting a process of expansion and so forth. Do these findings say anything about the viability of Big Bang-less theories of the universe?
They don't, in the sense that the distinct ideas that you're referring to, different alternatives to what we'd call the standard Big Bang model, still, all of these alternatives so far still involve the universe at some point having been at very, very high temperatures and very much more densely populated than it is right now. Under those conditions, what happened subsequently would have been very similar, and that includes the period where the Higgs condenses in the way that I spoke about. So the discoveries made experimentally, this week, say, and the decades prior to that, do not touch on those distinctions. As I say, there's sort of a continuity of thought from things that we can do in the lab, and see through telescopes, all the way to, our most speculative ideas. And you're, at the moment, talking about some of the most speculative ideas, which, however, leave fingerprints in the cosmic microwave background radiation. So they are also experimentally testable. But those two types of experiments have not contacted each other. So the Higgs boson has not yet impacted what we would see in the cosmic microwave background.
Now we have another question already here, but I'll call for further questions. Maybe this gentleman next. But yes, sir.
It was mentioned that in addition to 4 forces, gravitational, weak, strong, electromagnetic, there will be a 4th, Higgs force. But again, as was mentioned, that uniting theory that standard model that combining weak and electromagnetic fields. So in forces, maybe it will be more correct saying about the 3 forces instead of 5, when the electromagnetic and weak are like 2 different properties of the one force of the Higgs force.
So yes, exactly how you count. As I said, it really is like a family tree. In my mind, I think of the electroweak force as the mother of the electromagnetism and the weak nuclear force. Now, should I count that as mother, daughter, 2 daughters? I mean, so the counting is different, but what we really have unified, therefore, is the understanding. And what we understand is the Higgs boson and electromagnetism and the weak nuclear force fit together as one tight entity. And just to speak in ordinary English, we divide it up into different words and so on. And also the history of the subject had them separated. But we have now had an insight, which is now partly experimentally verified here. We have an insight into their deep unity. And, but you could make the case you made, which is that if that's one entity, then that leaves the strong nuclear force and gravity, and that's 3. And the excitement, as I said, one aspect of this is that information gathered at the Large Hadron Collider, as well as earlier experiments, certainly the Tevatron and even earlier experiments, may allow us to, in fact, there's already tantalizing hints that there may be this grander unification between the strong nuclear force and these 3 things that we just came together recently. And that the Higgs boson is a prototype for the kind of, grander Higgs bosons needed to affect that kind of unification, even grander unification. But yes, the counting depends on how you want to sort of count.
Okay, so this gentleman down here was next. Are there any further questions from the young people, the students in the audience? It's almost certain there'll be a question on the Higgs boson on the end of year exam, surely. Get in early. So, all right, yes, sir, please go.
Thank you, Professor David. Appreciate it. You always lovely, and you do a different program, especially I benefit for us. Thank you so much. And congratulations for every scientist, and appreciate it for that. I support that. I wish you can more search about brain, about antimatter and matter and universe. I wish you successful. We support you. And very, very important thing for, especially for me, an interested philosopher and science and metaphysics, very interesting. That may I go to a question because maybe everybody have time, space. Maybe I ask this gentleman, professor, how can Albert Einstein reject quantum physics, but why he tell nothing interesting, I want interesting, this mind the God, how can God mind the God work? And second question, if we create theory everything, do you think these are under physics? How can we create theory everything, include everything? When we create theory everything simple, do you think under physics? Thank you so much.
Okay, it was a very broad question.
Therefore, I shall take off any expert hat I have and speak personally, which is to say, when you have a theory when you have an enterprise which is trying to be as all-encompassing as saying, we're trying to solve the genetic code of the universe, and that really is the aspiration, and really we feel like we've unraveled very important pieces of it. I think we know that, and there's a lot to do. But when you have the ambition to do that, you sort of feel like, well, if it's that all-encompassing, it should include us in some way, okay? And in a reductionist approach, you'd say, okay, we're all made out of atoms, and the atoms are made out of these subatomic particles, and so on. And I have to confess that en route to then saying, does that sort of give me a sense that, yes, there are details, there's complexity, there's math I can't solve, but basically I understand the roots of myself, and somewhere en route to saying, yes, well, I can see sort of all the robot aspects of how my arm works and so on, and even how my thought processes work through electromagnetism, I think I see the continuity from the foundations all the way up to how thought works. But I do not personally understand where consciousness would come from. Not the thinking part, but the feeling part, which is maybe passive, but in a sense much more important to us, right? If this is just a robot and I slap him on the face, if he's programmed appropriately, he'll say, he'll try and defend himself and so on. But will he be feeling it? And so I don't understand where that fits in. I don't understand where that comes out merely out of complexity. So that might be my own failing of understanding, and it does come out in some reductionist way. I don't even understand where that could come out of the kind of enterprise we're in. So there's a mystery, and I confess it. Now, I think you had a broader second question, which was the end of physics. If we really managed to get this full program underway, and we say, here's the genetic code of the universe. Well, it's somewhat open-ended. It's like finding out how genetic codes work in the animal kingdom or the organism kingdom more generally. The kind of things people are talking about now, if we were eventually to get something experimentally confirmed like a string theory, very overarching ideas which combine general relativity with particle physics, Higgs bosons, all of that. People are already looking ahead, and they're saying, gosh, that kind of a theory, that kind of a DNA for our universe would have to be so well specified that it could, in fact, allow different types of DNA as well. Different combinations of the same DNA would allow other types of universes, and they would have to be outside there, outside our universe, or in the past of our, pre-Big Bang, or after our universe. So the fact that what we're calling our universe as a patch of space-time may be just one patch in a much bigger universe, a so-called multiverse, is already something out there. And then it's very challenging when we get to the 30th century AD, you know, how are we going to see a signal from, you know, the universe next door, okay? But these ideas are already, again, it's striking to me, these ideas that are already out there. There's sort of the theorists are racing ahead to try and look, you know, scout out what are the possibilities, and they're asking themselves, how do these things impact the LHC experiments? And you know, these conversations are raging in the halls of universities where they're trying to say, let's make it concrete, because we really don't like discussing angels on the, you know, pin of a needle, the tip of a needle. We really want to say, well, that's all fine, but bring it down to an experiment. What's your experiment? And but it's incredible, the ability of theory to really look ahead. It's incredible that nature has this unity that allows the human mind to understand it and to try and project a little bit ahead and say, how can we even bring the universe next door into our house and make a measurement in some clever way? So these things are happening. I don't know when it ends, therefore. I don't know whether there is sort of this sense, you know, the Nobel Prize winner Steven Weinberg in one of his books was talking about the idea of the world of discovery of fundamental physics as opposed to other kinds of physics where there's greater complexity. That the world of fundamental physics might be like the world of discovery on the globe, where there's some point where you've not studied every centimeter of the globe, but you know so much about it that you say, we've done it. We've conquered the surface of the Earth. And I'm not sure whether we reach that point in physics, again in the 30th century AD, or whether it can't be finished. I don't know what kind of enterprise we're in.
Thank you, Professor.
I might take the... oh, sorry, yeah, go ahead.
Counter comment. As an experimentalist, we take small steps because the steps have to be sure. And when we deliver a paper, that becomes a brick that's going to hold up a bridge. And so that brick's got to be solid. So when I hear Raman, the dreaming part is great. That's what drives us to do the science, all the thoughts that you can come up with. And anything goes. But when he delivers me a paper and I'm supposed to do something with it, that paper better have something specific. Look for this, because I won't understand the rest. But and then we'll do that. We'll take that small step, and that will usually tell us, well, okay, this direction's good, that direction's bad. There's been times in the past, several times, where we said, we're almost at the end of physics. It didn't happen so long ago. We thought, we're just about done. We just have these few little things. We don't understand black body radiation or things like that. And, you know, so we covered this globe, all except for this one little area that we hadn't mapped yet. And then we find out when we map that that's connected to this other huge globe. So, yeah, maybe we're going to be close.
Possible, not maybe.
Maybe, possibly. But we'll find out.
Perhaps
a lot of
I'll
work.
Use the chair's prerogative to insert a more mundane question after this very profound question with a profound answer, which has to do with money. The great I.I. Rabi lamented the fact that he felt that physics was becoming the property only of the very wealthiest nations who could afford to build these big machines, and he thought that wasn't reasonable because physics should be the property of everybody regardless of their wealth. So are there a lot of politicians around the world groaning at the moment thinking, oh no, the physicists have finished, they've done the Higgs boson, they'll be knocking on my door tomorrow to ask for more money to build the next machine?
I can actually say something to that because I'm responsible in the region here for on the northern hemisphere for Southeast Asia. Now, Southeast Asia is typically not a region like, you know, Thailand or Singapore or something. They will build their own accelerators. But there is an enormous awareness now, actually, of the importance of science and of fundamental science. Even in Singapore, where they're very, very pragmatic, rather than maybe thinking in fundamental ways. And in the experiments which we both represent here, we have been directly contacted already by groups there to join the experiments. Of course, they can't build such an experiment at home. And they shouldn't be doing that because we have the accelerator, we have the experiments, but they can partake in it. And thanks to, I would say, modern technology and telecommunication, it becomes possible. The people can actually, from their country, maybe with some training coming to CERN, but in their country, do an experimental program on the experiments. So we're becoming, in the last 10, 20 years, really global with these kind of major enterprise and major experiments. And we can enter the world in that. And even now countries from Africa start to get that interest. I would think they would have maybe other problems first, but they feel that the need is there that for this intellectual development to be part of it. And just last week, in fact, we had a new member. To give you an idea, in CMS has now, I think, 42 countries from which we have institutes which are participating in this experiment. Similar number for Atlas. Last week, just before I came here, Thailand was a new member of the experiment. And on my way back from here, we're going to pass through Hong Kong and Singapore, in fact, for further negotiation. So yes, we are actually involving. It's more and more people of the world in it.
Wonderful story. Did you want to add?
Yeah, I think if I look at, you mentioned that whether there's any issues about supporting the fundamental physics or basic science. If I look at countries like China or Korea or India, in fact, there's a big push to really supporting fundamental and basic sciences. So I think depending on which countries, you may have different issues, but I can see that some countries who are not very, very strong in basic science, now they see the excitement and they see opportunities to really make a big impact on that.
Okay, that's wonderful. So maybe I'm conscious of the time and I'm going to get into trouble if I don't wrap up shortly, but maybe I'll call for one further question. The gentleman right in the middle, if you can get the microphone.
First, I'd just like to thank all the speakers and the panel for an excellent presentation and quickly ask a couple of related questions. I don't seem to have read very much about the other bosons, the W and the Z boson, and even some of the other heavier particles in the standard model contributing to, in their non-quantum manifestation, conferring mass on other particles that pass through their fields. Is there anything in that? And the other question is, what we have seen is a particle round about the 130 multiplication of the proton mass, and it's a Higgs boson, sure. If you're going to look for another Higgs boson, how big, how many multiples of the proton mass would you expect it to be?
Okay, that was a long question, but perhaps can I ask for a short answer?
Could I just, so there are experimental limits on other Higgs boson masses, not just this object that now is not limited, but actually seen. But beyond that, there is, if it's going to be a Higgs boson, then there's just a ballpark that we know, which is in the ballpark of hundreds of times the proton mass. But there's not a specific prediction. That's why we need experiments in this case. They have to lead us. It's not a theorist who can say 10 decades in advance, look here. But there is this ballpark, and that is well within the scope of the LHC to do. Now, I already, in my sleep-deprived, jet-lag state, forgot the earlier part of your question, which maybe keeps the answer pretty brief. I don't know.
I think that's great. I mean, I think this topic is essentially open-ended, and ladies and gentlemen,
Can I just ask
yeah,
one thing?
Of course.
Is there a student question at all? Can
Yes.
you just, is there somebody who...
Yes, I think the first hand was just here. So let us wrap up with a student question.
You know how the Higgs particle gives mass to particles, and then you say it's 125 times the mass of a proton. How does it have a mass itself?
So that's an excellent question, and in some sense, you know, you have to ask, why is it that having a mass needs an explanation? You know, why can't you just have one? And that comes back to this story of electroweak unification. And so there are two aspects to particle physics, like there are two aspects to playing marbles. A marble has two things it can do. It can travel, and it can bounce off other marbles, okay? Interactions and traveling. Particles can interact with other particles, and they can also travel. If you study just the interactions of particles, that's where you see that they are beautifully in accord with electroweak unification. That is, there's something about electromagnetism and the weak nuclear force which are really intertwined, and if you just study the body of interaction strengths, you will just see, with the right eyes, you'll see that there's this intertwining, which is what I'm calling electroweak unification. The paradox for a number of years was, in the 60s, that if you look at the propagation of particles, the central thing that relativity tells us that governs how they propagate is you put in this much energy and you can travel this fast, which seems reasonable enough, okay? And how fast can you travel for a given budget of energy? That is determined by one number, your mass. That's what mass is to a relativist. And it turns out that electroweak unification, which is obvious once you look with the right eyes at this incredible body of data we have, predicts something for the masses of particles. It's a fantastic prediction. It predicts the mass of every single particle seen until this week. And that prediction is they should all be massless, okay? So the paradox of the 1960s was, only amplified in the subsequent decades, all interaction strengths show you electroweak unification, and all the masses of elementary particles show you that that unification predicts something nonsensical, which is that they should travel at exactly the speed of light and they should have exactly zero mass. The Higgs mechanism, the Higgs field, is something that slows them down. For example, do you know that light itself, when it travels through water, travels slower than the speed of light in vacuum by a tiny amount, but it still travels slower. So invisible things can actually slow you down. Try swimming in water. The Higgs field is something like that. Different particles swim through it with greater or more efficiency, and it's measured by this mass. So now I've already lost the thread of the question, but yes.
Why does the Higgs have mass?
Oh, why does the Higgs mass? Now it turns out that if you study the theory of the Higgs field and how it does what it does, you find that the Higgs field is actually not, it is not predicted by electroweak unification to be massless. It doesn't need a reason to have a mass. In fact, this is the flaw of the minimal standard model, that if you take the minimal standard model and you study what is the sort of generic expectation for what the Higgs mass should have been, it would actually have been many, 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 trillions of times heavier than it actually has turned out to be. That's the generic expectation. So there's actually a puzzle that still remains, which is why many people think the minimal standard model is actually wrong from a theoretical viewpoint, which is that the Higgs boson has no reason to be massless. In fact, it has every reason to be much more massive than it just showed up being. And the puzzle is to figure out why. And that's why many of us think that there's something beyond the minimal standard model. And that's why the job of the LHC and the rest of particle physics, that job has only just begun. That's what I'd say.
To add one more puzzle, is that those neutrinos, they seem to be also something bizarre. I mean, first of all, their mass is extremely tiny. the electron mass is very, very tiny, about 1,000,000 times lighter than top quark. And neutrinos, they are about 1,000,000 times lighter than electron. So you can see how tiny they are. And also their behaviors are very different from other kind of particles in the graph I showed earlier. So the question is that whether neutrinos, their masses are really coming from Higgs or not. That's also a big question, may not be. So origin of neutrino mass is another big question that our particle physics field is looking after.
Okay, well look, I think that's a good note to end, because we have seen there is a vast number of puzzles, very profound, very exciting, very interesting, still to be solved. We have a number of candidates in the audience for the next Director General of CERN, or in a generation or two, and I invite you to stay tuned and to participate in this great human endeavour. Before I end, I'd like to thank Carolyn Hamilton and her team from the Centre of Excellence for Particle Physics at the Terascale, who've worked so hard to pull all this together, and the support staff who have helped us out with the audio-visual. And I would also like to thank the audience for coming and for their excellent questions.
And extend an invitation to them.
You may.
I know there were more hands that were up before. Tomorrow at noon, we're going to have a dedicated session in our conference at ICHEP with what's called a Google Hangout. Now, I know these guys all understand that. There's something out there on social media called Google+. And if you go on to that, if you go to Google and go to Google+, and you look for CERN, we will on there have a Hangout. And that means that you can go there and click and join us. You can either watch people ask questions, or if you have a question to ask, you can ask it. So tomorrow at noon, we'll be doing that in our session. We have more experts who will be able to answer any other questions that you have. Okay,
excellent. Thank you for that. And also, we have a program for the rest of July, which I would also like to invite you to come along to. You can find the program also on the School of Physics website if you want to just check the details. So thanks again for coming, and thank you, panel, for dealing with these difficult questions, but giving us an insight into your personal participation in this great endeavour. Thank you very much. Thanks for coming, ladies and gentlemen.